Color properties of light sources. The color temperature of a light source is measured and expressed by the chromaticity coordinates, x, y, or u, v, or u, v, for that source. 1 The color of white light sources can also be expressed in terms of the correlated color temperature, CCT, having the unit Kelvin, K. The CCT of a test source is defined as the temperature of the black body, or Planckian, radiator having a source color that matches, as closely as possible, the color of the test source. Correlated color temperature, CCT, is a widely used term to identify the appearance of near white light sources, as well as screen white on computer monitors. It is usually the first color parameter specified in lighting system design, since the color of the source has a profound influence on the atmosphere created by the lighting. The CCTs for modern lighting systems are generally in the range 2700 K, correlating with traditional tungsten filament lamps, to 6500 K, which is the color of full midday daylight in summer. Most domestic users prefer warm lighting in the 2700 to 3000 K range, while educational and commercial installations more commonly use the cooler range, 4000 to 6500 K. Note that warm and cool here refer to the psychological ambience of the lighting in contradistinction to the values of CCT. Technically, the CCT is defined by plotting the color of the source on a CIE, U, V, graph to determine the closest point on the Planckian locus, and the value of the temperature at that point gives the CCT. Coming now to color rendering, the three previously mentioned systems, represented by the indices Ra, Qa, and Rfrespectively, have a number of elements in common as well as their own distinct features. Their most important common feature is that they all produce scales in which the maximum is 100 for the best sources. The Ra scale is open-ended at its lower end, and can run to negative values, whereas the other scales terminate at 0. The Ra scale was originally designed to provide a measure of the relative merits of the fluorescent tube sources, being widely adopted in the 1960s, and the other two scales have been normalized in the sense that they have been scaled to provide the same index values for the original set of fluorescents. The two later scales do, however, diverge considerably from rain assessing other newer sources, particularly LEDs. The next main factor they share is that they are all based on the comparison of sets of test colors which are illuminated in turn by a test light source and a reference source of the same CCT. In all three cases, the reference sources are chosen as Planckian radiators if the CCT 100, or a decrease, RG 3 dimensions is considered by Weigla and Banks using a recursive technique to split n-dimensional cells into n-simplexes. The resulting surfaces exist in 4 dimensions and are able to be displayed using two techniques, stereographic projection, section 4.1, or slicing to reduce dimensionality. It is noted that the centroid division technique used to break cells into simplexes used in this work is suboptimal, see Table 7, but can be improved using lookup tables similar to those used in marching cubes. The technique was used to compute the swept volumes of time-varying data generated from electromagnetic field simulations, allowing them to be displayed as animations. Properties of hypercubes in dimensions 0 to 4. Number of simplexes generated using differing subdivision techniques in n dimensions. Extending MC into the fourth dimension, and beyond, was explored by Banaramka et al. At the time of the report, a relatively small amount of work had been conducted in studying isosurfaces beyond the third dimension. It was found that by extending MC into 4 dimensions, the lookup table, following removal of symmetrical configurations, required 222 separate configurations. As with the 3D variation of MC, one aspect to be taken into consideration is the dealing of ambiguous configurations. A mathematical proof of correctness is provided to verify that the topological structures generated are valid. An example use of this algorithm would be to present volume data with a time dimension by selecting 3-dimensional slices of the hypervolume.